Large language models are everywhere, powering everything from healthcare diagnostics to financial forecasting, from educational tools to autonomous mobility systems. At the heart of their intelligence lies the transformer architecture, a design that's revolutionized artificial intelligence over the past few years. But while attention mechanisms have been widely studied, how tokens relate to one another across a sequence, there's a critical piece of the puzzle that's remained in the shadows: the feed-forward network, or FFN. In modern LLMs, the FFN is responsible for about 2/3 of all parameters. Yet despite its massive scale, it's one of the most misunderstood components. Why? Because it operates on a complex context-dependent input, a blend of self-attention output and residual stream, that evolves across layers, making it nearly impossible to interpret. This is where MemoryLLM comes in. Proposed by researchers at Apple, including Ajay Jaiswal, Lauren Hanna, Hanbyle Kim, Duck Hong, Arnav Kundu, Mayaded Farajtabar, and Minsik Cho, we introduce a radical rethinking of how FFNs function in transformers. Instead of treating them as black boxes embedded in a dynamic flow, we decouple them entirely from context and train them as context-free neural retrieval memories. Here's how it works. In a standard transformer, each feed-forward layer receives an input that's not just the original token embedding, but a transformed, context-rich representation shaped by prior attention operations. This means that the same token, like coffee, might activate different parts of the FFN depending on whether it's in Jack loves coffee or the coffee was cold. That makes it impossible to trace what the FFN really knows about coffee in isolation. MemoryLLM solves this by training every FFN module directly on raw, token-indexed embeddings, static vectors corresponding to each word in the vocabulary. No attention, no residual stream. Just pure input-to-output lookup. This simple but profound change unlocks two major breakthroughs: interpretability and efficiency. Let's unpack the first. With static discrete inputs, each token ID mapped to a fixed embedding, we can now ask, which memory cells does a given token access in the FFN? And more importantly, do semantically similar tokens access similar memory locations? To answer this, we developed the TKV framework, token key value. In this model, the FFN's up projection matrix becomes the keys, the down projection matrix the values, and the gate projection acts as a learned reweighting function. For any input token, say Jack, we compute a set of memory coefficients, how strongly each key contributes to the final output. Then we retrieve the corresponding values, weighted by those coefficients, to produce a contextualized output. The result? A fully interpretable neural memory. And when we visualize these key contributions across the entire vocabulary using TSNE clustering, we see something remarkable. Semantically similar tokens cluster together. Personal names form tight groups. Geographic locations group by region. Punctuation marks a line by function. Even linguistic properties like tense or part of speech emerge naturally. This isn't just theoretical. It means we can now inspect what knowledge the model has encoded and even edit it, like selectively modifying the memory of climate change or vaccines without retraining the whole model. But the benefits go beyond insight. Because the FFNs now depend only on token embeddings, never on intermediate hidden states, we can precompute their outputs once, store them as static tables, and load them on demand during inference. These are called token-wise lookups, or ToLs. Imagine a lookup table where every word in the vocabulary has a precomputed FFN output across all 24 layers of the model. Instead of computing the FFN every time a token appears, we just look it up, like a dictionary. This transforms inference from a compute-heavy process into a memory-efficient one. And here's the kicker: VRAM usage drops dramatically. Since 2/3 of the model's parameters are now static lookups, we can offload them to storage and load them only when needed. This enables plug-and-play memory management, removing layers from VRAM based on importance, or caching only high-frequency tokens. This is not just theoretical. We trained MemoryLLM at 250M, 750M, and 1B parameter scales. The results were striking. On retrieval-heavy tasks, like Wikitext 2, LAMBDA, or CQA, MemoryLLM performed nearly as well as full transformers, even when we reduced the FFN contribution to just 50%. But on reasoning tasks, like Winagrand or BoolQ, performance dropped more sharply. Why? Because the FFN isn't doing logic. It's doing retrieval. It stores facts, patterns, and associations. It's a parametric memory bank built from the training data. So when we remove FFN influence, recall-based tasks suffer. But reasoning tasks, those requiring synthesis or deduction, were less dependent on it. This insight reveals something profound. LLMs are not just reasoning machines, they're also retrieval systems. And the FFN is the engine behind that retrieval. Still, there's a trade-off. MemoryLLM, while interpretable and efficient, underperforms standard dense transformers when it comes to overall accuracy. Why? Because it lacks the ability to adapt FFN outputs to context. That's where Flex-MemoryLLM comes in, a hybrid architecture that bridges the gap. Instead of making the entire FFN context-free, Flex-MemoryLLM splits its parameters into two parts. FFN compute, FFNC, a context-aware module that processes the residual stream, preserving the model's full computational power. FFN memory, FFNM, a context-free lookup module trained on token embeddings, just like in MemoryLLM. By tuning how much of the FFN is dedicated to memory versus computation, we can control the balance between efficiency and performance. We tested this across 1B scale models. The results: Flex-MemoryLLM with 704M active parameters, just over half the size of a standard 1.2B model, achieved performance that surpassed the base model in some benchmarks. And as training data scaled from 25B to 150B tokens, the performance gap between Flex-MemoryLLM and the base model shrank dramatically. Even more impressively, when compared to traditional pruning techniques, like magnitude pruning or sparse GPT, Flex-MemoryLLM consistently outperformed them at the same active parameter count. This suggests that architectural innovation may be a better path to efficiency than post-hoc compression. So what does this mean for the future of LLMs? MemoryLLM and Flex-MemoryLLM aren't just academic curiosities. They represent a new paradigm, designing models not just for performance, but for transparency, modularity, and efficiency. We can now pre-compute, offload, and inspect the knowledge stored in FFNs. We can edit memories without retraining. We can deploy models on edge devices with limited VRAM. And we can finally ask, what does the model really know? This is not just about better models. It's about understanding them. And in a world where AI is becoming ever more powerful and ever more opaque, this kind of interpretability isn't just valuable. It's essential. So the next time you use a language model, remember, behind the scenes, there's a vast hidden memory system. One that, thanks to MemoryLLM, we're finally beginning to see.